Hi everyone, my name is Andrew. I'm the 2019 TA for NANO 202. So I'm here today to introduce the computational component of the course. What the computational component is it's a program that I've written that focuses in on the intermolecular forces portion of the class. So in particular, what we're looking at are the van der Waals forces. That's the CECM, the Debye, and the London interactions. So the dipole-dipole, dipole-induced dipole, and the dispersion interactions. So what I've done is I've created a code in Matlab that tries to model, first I have two components that just look at the CECM interaction, just looks at the interaction of dipoles with each other, permanent dipoles. And then I've got a further portion that puts all of the forces together, and so that's going to include all the CECM, the Debye, and the London forces. So this is not meant to be a computationally intense assignment. All I'm trying to do is give you some broader perspective on, first of all, what tools are out there to look at intermolecular forces. But I'm also trying to sort of illustrate some of the concepts in the class. So hopefully through this assignment you'll learn something about angle averaging of dipole and how that affects dipole interactions, something about many-body interactions, and things of that nature. So let's get started looking at some of the code. So we're going to talk a little bit about functions because functions are going to be the real meat of the computational assignment. So I'm going to introduce the concept of a function and then talk a little bit about how they're actually implemented in MATLAB. So what is a function? So in computer science terms, you can think of a function as being sort of like a machine that takes in some values, modifies them in some ways, maybe combines them, and spits back some values at the end. So here we've got a simple function. So this is the script that's going to what we say is call the function. All right, so we've got our function called quadratic, and in parentheses we have the values that we're giving in, the values that it's going to take in, and then it's going to modify. And we're setting a variable called new number equal to what this function is going to spit out. So this is called calling the function again. All right, so what's our actual function and how do we write it? So our function is called quadratic, so we've got a separate script. So the first thing in a function is the word function. Just tell MATLAB that what we're doing next is creating a function. Then we've got brackets right here. So if you'll remember, brackets in MATLAB define a list. So a bunch of related variables. And then in this case, we've only got one variable in here called square. So what this list is all of the variables that at the end of the function it's going to give back. So we call that what the function returns. So in this case, we're just giving back one variable, which is called square. All right, we say that's equal to, then the name of the function, quadratic, and then in parentheses, we've got the values, the variables that are being given to the function to modify. So in this case, we've decided to name, it's only getting in one variable, and we're saying that it is called x. All right? So after that, we go down, and so it's important. So it's going to, this function at the very end is going to look for a variable called square, and that's what it's going to give back. So at some point in this function, we have to make a variable called square. So we do that here, and we set it equal to x, which was the value that was given in, squared. So this is a fairly simple function. So what it should do is take in a number, x, and then return that number squared. So what happens whenever we actually run our test script where we call the function? So it's going to give in a number, 2, and set this variable new number equal to 2 squared. And when we run it, that's what we get. New number is equal to 4. All right? So this doesn't, so it's important that functions do not just have to bring in just one variable, and they do not have to give out just one variable. So we can see that with a different function, which we call sum and multiply, This is the script that is going to call the function sum and multiply. So the function sum and multiply takes in two numbers separated by a comma, 2 and 3, and it's going to give back two numbers, sum1 and mult. All right, if we look at the actual function, we've got the same sort of format over here. So it's taking in two variables, x and y, and at the end it's going to give back two variables, sum1 and mult. And it's going to give those back in the same order that they're written here. So the function at the end is going to look for these two variables, sum1 and mult, to give back, so we have to define them. So sum1 is equal to x plus y, and mult is equal to x times y. So if we're giving 2 as x and y is 3, whenever we run this, what we should see is that we get back sum1 as 5 and mult as 6. So now let's get into the meat of the computational assignment, the actual files that you've been given. So you'll notice that there are a lot of files on the left-hand side, but you're not going to need to worry about most of them. Actually, you're only going to need to care about 4 of them at all, and you're only going to need to code new things for 3 of them. So let's look at the main function, the one that you won't have to code anything for. This is just the actual function that you run, and that's called GUI3. So that stands for Graphical User Interface, and then it's the third one that I coded. All right. So what we're going to do whenever we want to actually run our program is go to GUI3, open that up, and just hit run. What's going to pop up is a screen that should look something like this. So you're going to have a bunch of variables on the left-hand side that you're going to be able to change, and then you're going to have a drop-down menu of the different types of simulations that you can run and that you will need to run for the computational assignment. So if we want to do, say, 2 static dipoles, that's the first section of the computational assignment, wherever we have 2 polar molecules that are fixed in space. And so what we can do is we can set things like our temperature, the strength of the dipole moment, and in order to actually look at our simulation, we just hit run. All right. Then over time, we'll watch as our simulation progresses. And here we go. So we're just watching over time the evolution of our system. So I want to give you guys some context into how these dipoles are actually moving. So what's going into this sort of angle averaging effect that you should be able to see. So what we're actually doing is a Monte Carlo simulation. So how does a Monte Carlo simulation work? Well, say we've got 2 molecules in a system. So they're in some sort of initial configuration. Right? So we've just got molecule 1 and molecule 2. So what we're going to do is we're just going to slightly perturb one of the molecules here. So let's choose this one. So we're going to say it can move in any direction randomly up to a certain distance. So it moves, and we move it so that it's here to here. So these 2 particles, we've set it up so that they're interacting by some sort of potential. It could be a Lennard-Jones potential, it could be some more complicated van der Waals potentials, but their interaction by some potential. So we can calculate then, using our potential law, the energy in the initial state, we'll call that U, and the energy in the new state, we'll call that U prime. All right, so we can then calculate that change in energy, delta U equals U prime minus U. So using that change in energy, we're going to use some sort of algorithm to decide whether we want to keep this change that we made or keep the system in the state that it was already in whenever we started out. All right, so what we use is something called the Metropolis algorithm. So basically what that says is the probability, P, that you make the change we have two different conditions. So say that the change in energy is favorable. So you've got U prime is lower energy than U. In that case, this quantity is going to be negative. So if delta U is less than 0, then the probability is just going to be 1. All right, simple enough. We then, though, if this is an unfavorable move, we don't want to just completely eliminate all unfavorable moves because of thermal fluctuations, things do sometimes randomly move into unfavorable enthalpic configurations. So we're going to assign a probability if delta U is greater than 0. We're going to say that it's equal to the Boltzmann weighting of it. So we've talked about the Boltzmann weighting before in class, and that is e to the negative delta U over kt. That might be a little hard to see, but that's e to the negative delta U over kt. So basically that says that it's the probability that we accept that is somewhat dependent on the thermal energy in the system. So if there's more thermal energy in the system, it's easier for the system to randomly move into one of these high energy states. So this is how the dipoles move, is it just does this over and over and over again. It moves one of the dipoles, sees if it's energetically favorable or not, decides whether to accept or reject, and then it does the same thing to the other dipole. And it rotates through them again and again, and it just moves them around. So after that, we're going to look at many static dipoles. We're not going to have to do that much coding for it. So I'm not going to go through that too in depth here. The other type of simulation that we're going to run is two moving and many moving dipoles. So it's a similar idea, except we're no longer fixed in space. And now it's going to look at not just the key-sim interaction, which was all we were looking at before, but we're also going to include the London and Dubai interactions. So two moving dipoles looks something like this. And over here on the left-hand side, before you start running, you should be able to change any of the variables that you want in the system in exactly the same way. And note that a lot of the times the arrows, so the arrows represent the orientation of the dipoles. They can be quite small, so make sure to wear your reading glasses. So let's talk a little bit about how once we move from the static molecules to the molecules in motion, how we're actually going about making those molecules move. So what we're doing here is basically a molecular dynamics simulation. So molecular dynamics is different from the Monte Carlo simulations we were talking about before. The fundamental part of a molecular dynamics simulation is the force. So we're going to think about everything in terms of forces. And we're going to use Newton's second law. So if you have the force, you can use that to find the acceleration. And as I'll talk about in a minute or two, we're going to be able to use the acceleration to find all of the new velocities and positions of every molecule, always moving it forward through time. And remember, since what you're doing is you're coding in the energetic potentials for the key-sim, the Dubai, and the London forces, you're going to be getting the energies. And remember, energy is just the force is just the derivative of the energy with respect to position. So you're going to have to get both the forces for the molecular dynamics portion of the simulation, as well as the energies for the Monte Carlo. Remember, in the Monte Carlo, we had to compare the relative energies to each other. But for molecular dynamics, we're always looking for these forces. Okay, So once we have our forces on the system, so presumably all of the code you'll have written will generate all of these forces, what do we actually do in order to move our system forward through time? So don't sweat this too much. This is mostly just if you're interested in how the system works. If not, you don't have to do any actual coding for this part of it. All right, so we use what's called the velocity Verlet algorithm. So this works really well for both keeping the motions of the particle stable as well as the velocities of the particle stable over time. So the way that we write this out is x of, so we say we're doing some numerical integration. So we're saying we've got our positions, x, and we're moving forward a little bit in time, some delta t forward in time. All right, so at our new time, the positions of the molecules are going to be equal to the original positions of the molecules. That's x of t. And this should have a little guy up here too. Plus the velocities at the original time times delta t. So that's some numerical integration there. And then we're going to also add 1/2 of the acceleration at the original time times delta t squared. All right? And the way we're going to update our velocities is we've got our velocities at new time, our original time plus a small increase in time delta t. That's going to be equal to v of t plus the acceleration at the old time plus the acceleration at the new time over 2 times delta t. All right. So this is a little complicated and a little weird because we've got both the acceleration at the old time and the acceleration at the new time as as things that update this velocity. So how do we actually go about doing this? So if we actually look at how this is implemented, and you can see this in the calculate VDW function, this is actually implemented in there. So we take first our velocities, and we're going to half update them. So we do this, the reason that we do everything in this order is it keeps it so that we only have to keep track of one set of velocities at a time, one set of accelerations at a time, and one set of positions at a time. So you'll see how that all pans out in a second. So we do a half update. And we're going to set that equal to the original velocities plus 1/2 a of t delta t. All right. So basically, we're taking this part and we're taking care of adding this portion and this portion. So we've half updated it. All right. So we've moved it forward halfway of what we want to update. And we can completely overwrite our old VT now, because what we can do is we can update our positions completely. So we're moving it all the way forward to our new position in time. And we can just set that equal to x of t plus v of t plus 1/2 delta t. So this is our halfway updated velocities that we've got up here that we just calculated times delta t. And you'll see that this expression for the halfway updated velocities is going to include both this original v of t, right, plus 1/2 a of t times delta t squared. So we've actually taken care of everything here, everything that we need to do fairly simply by just plugging in our new half updated velocity. What we're going to do next is we're going to update our accelerations. And so we're going to just do that from our intermolecular potentials and forces. All right? So we're going to do that from forces. So again, these are those Keesom, London, and Debye interaction potentials and the forces that you're going to be coding into the simulation. All right? And from those, we just use Newton's second law in order to get the new accelerations. Just divide it by m. All right? And then finally, we're going to fully update our velocities to t plus delta t. And that's just, we're going to do that by taking our half updated velocity and we're going to add on our updated accelerations. All right, and so that takes care of this component of our full expression here. So now we've added on, first we added on the original acceleration, and then after updating, we've added on the new acceleration. So we've fully covered all of this. So this is how the simulation moves forward through time. This particular algorithm is used, it saves memory, it's very stable for these sorts of simulations, so this is why we use it. So now let's look at the three functions that you'll actually be editing over the course of the computational assignment. So remember, I'm not trying to make this really tricky for you guys. I just want you to be a little bit familiar with programming, but most of the actual questions on the computational assignment are about interpreting your results. With that said, let's get into what we're looking at. So there are the three functions that you need to edit, and they correspond to the three components of the van der Waals force, and that's Keesom, London, and Debye. So the first two portions of the computational assignment will only use the Keesom, while the next two will use all three. So let's look at the setup of our functions. So here's the function for Keesom. So remember, on the left-hand side are the things that the function will need to give back. So these are things that you're going to have to calculate inside this function. All right? On the right-hand side are things that you'll be given, basically. Down below in the comments are what all of these variables are that you're going to be given and what they should look like. So the variables that you're going to be given in calculating your Keesom forces and energies are x, where x is a n by 2, where n is the number of atoms in the system. So it's going to be a vector or a matrix, n by 2 matrix, holding the positions of the atoms. So the x component of position is in the first column and y is in the second column. So if we had 3 atoms in our system, if the first one was at 0, 1, the next one was at 1, 2, so that's x, y, and the next one was at 2, 3, that would be the x matrix, and if we wanted to get the position, the x component of the second atom's position, we could say x, and we said it was the second atom, and we want the x component of it. So we'll get back the x component of the second atom. All right. We also get u. If you remember from looking at the interface, you can set the dipole moment. So u is the strength in the Debye's of the dipole moment of all of the atoms or molecules in the system. Dipoles, so that's going to be a n. Remember, n is the number of atoms in the system, n by 1 vector, which holds all of the current angles of the dipoles. So in this case, so if we had 3 atoms in the system again, the list could look something like one dipole is oriented 180, one is oriented at 75 degrees, and one is oriented at 30 degrees. And all of these, note, are relative to 0 being in x-axis. So they're not relative to each other, it's relative to some arbitrary x-axis. Finally, you're given J. So J is the index of the current atom being calculated. So it's a little complicated, but it's just it tells you which one of the atoms you're currently calculating the force for, because in the key-sum function you're only calculating the force and the energy on one atom in your system. So you'll see that under the return. So W is the total dipole energy of the atom in the current dipole conformation. So you're just going to give one number, that's the interaction energy from the key-sum force on the atom J. All right, so that's important. So J is going to go back into, you're going to use J to look at X at certain points in time. So you can imagine if you wanted to find where the position of the atom is that you're currently calculating on the force on, it would be the position matrix would be given by X of J. So that's where you're going to be using J. All right, so so you're looking at the energy on just that jth atom. Never say the word jth in normal day-to-day conversation. It's sort of weird to hear. You're also going to be calculating the force. So similar, but remember, force is a vector compared to W, which is just a value. So force has some sort of direction. So you need to store this in a 1×2 matrix where you have the x component of the force and the y component of the force. So you should be setting F equal to, if your x component of the force is 100 newtons and your y is 2 newtons, then you're going to give something back in this form. All right. Finally, you're going to turn back W norm. So this can be somewhat confusing to some people. All this is effectively is everything in W, but you get rid of the R component of it, the R dependence of it. So you no longer are looking at the distance dependent part of it. You're just looking at, so if you wrote everything out as C van der Waals over R to the 6th, you're just looking for that C component related to the key-sum interaction. So that's what W norm is. You're basically just going to be rewriting W and not putting the over R to the 6th part of it. Okay, so that should be, so that's the key-sum force. The London and Dubai are fairly similar. They're quite similar to each other. The main difference is that compared to the key-sum force, for reasons that are a little bit behind the scenes, instead of just looking at one atom at a time, just this jth atom like we do for the key-sum, we're going to look at all of the atoms, and you're going to calculate all of the energies and forces on all of the atoms. So in comparison to before, wherever you were just turning back one value for W, you're going to give back a n, where again n is the number of atoms in the system, by one vector of all of the London energy for each atom in the system. So if you have 3 atoms in the system, and the energy from the London force on the first is 3 kilojoules per mole, the second is 2 kilojoules per mole, and the third is 1 kilojoule per mole, you're just going to give back something like 1, 2, 3. Okay? You get in slightly different values. In this case, you also get in the polarizability denoted by alpha, ionization potential as denoted by I. But besides that, everything is going to be pretty similar. And again, you have to give back W norm. In this case, that's the C London parameter, or sorry, the C London constant that you would use in a force calculation. So key-sum, London, and Dubai, all fairly similar. So let's look at two components of this that have been actually filled out in a model style. So for not real intermolecular forces, but let's say that we're scientists and we've recently discovered a new intermolecular force called the Lipome interaction. All right, so we're getting in almost all of the same information. So this is done in the style of QSIM, where we're only calculating the energy and forces on a single molecular atom based on its dipole-dipole interactions. So the Lipome force is one that's similar to the QSIM, is related to its the relative orientations of dipoles of a polar molecule. So what you can see is we start out with all of the same initialization, where we set everything equal to 0 at the very beginning. We set up a for loop, so we're going through every component of our position matrix X. And if I is not j, so remember we're calculating the force on the jth atom, so we don't want to set up an interaction between the atom and itself, so we're going to skip that one. But then we're going to find a r value, the distance between the jth atom and whatever atom you're looking at that point. You're going to find a theta naught, so that's going to be relative again to the x-axis. What the angle between those two positions are. So be careful here. You've got this conversion term because you need to convert everything into degrees. So then you also have two extra thetas. So those are the angles, the angle between each dipole and the line basically connecting the positions of those two atoms. So if you go back and review the QSIM interaction, you should see where this theta 1 and theta 2 come into play. All right. So then we calculate our energy. So it's just we take our initial energy, we started it out at 0, and we subtract from it because it's an attractive force. And then here's our expression for the Lipome force, which is something along the lines of the dipole moment cubed, something long and complicated down here. It's got an r⁴ dependence, and then this part of it, which again should be similar to what you see in the derivation of the QSIM interaction. All right, and note here cos d versus just cosine. So this is a mathematical function that if you give it some angle, it returns the cosine, but it takes it in terms of degrees. So that's why it's cos d. Regular cosine does things in radians, and things will get all screwy for you. Okay? And since dipoles is given all in degrees, you need to make sure theta naught is also in degrees. So just do everything in degrees for ease of use. W norm, we're doing the same thing. Remember, this is just the C component. So all we do is we copied all of this down, and we just get rid of that R dependence. We don't put that R dependence over here. Okay? And then we do the forces. So the x component of the force and the y component of the force. So this is just the, we differentiate W with respect to R. So we'll have a r to the 4th dependence down on bottom because we've differentiated it. We've also got a 3 out here. And then we just spatially break it down into x and y components using cosine and cosines and sines. So if we want to look at how this actually runs, we can go to the Lipome example. And this should look something like that 2 static dipoles that you'll be coding in for in your actual assignment. They're just going to flop around for a little while. We'll watch them. We'll see how well they orient with each other. So that's going to be, again, the principal part of the principal component of this computational assignment is looking at the outputs of your simulation and trying to explain in terms of intermolecular forces what's actually going on in the simulation and why this might be occurring. And they keep on flopping around for a while. You know, it's a good time to go grab some coffee, maybe some tea, a LaCroix if you care to. All right. And now we've come to the end of it. Okay, and we're going to look at just one more example over here. And so this one is in the style of the London and Dipole functions. So we've got, so instead of giving back just the energy and forces on one, we're going to calculate all of them, all of the energies and forces for every atom in the system, all within this one function. So we're not just looking at the jth atom, we're looking at all of them. So the way that we do that is that we do almost the same thing that we did in the Dipole function, but we're going to do two loops instead of just one to go over every atom in the X matrix. So we're going to go over every I, wherever every atom in our position matrix X, and then we're going to go over every atom again and set a second variable equal to J, going over every atom in X. If they're not equal to each other, again, we don't want to calculate intermolecular forces between atoms at themselves because that's no longer intermolecular. Also, everything will explode because you'll divide by 0. So we're going to make sure I is not equal to J. And we're going to do the same sort of stuff. We're going to find our R, our distance between the two atoms. We're going to calculate, instead of W, we just do W of I, of the ith atom that we're calculating the force on. But besides that, everything is almost the same. Same thing, we've got our normalized W and our I component of it. And Fi2, because this is a multi-dimensional matrix now, Fi2, Fi1 and Fi2, again broken down into X and Y components. And do note at the end of these, we also normalize W over the number of atoms it's interacting with. So it's going to interact with every other atom in the system, so that's length of X minus 1. So we also actually did this in the Dipole function. So that's just because we're trying to get the C component of it. It shouldn't be dependent on the number of atoms it's interacting with because it should be some sort of constant. So that should just about sum it up. One other thing that I'll point out is that for the KeySim and London and Dipole, it'll also print out a plot of that W norm of your C value over the course of the simulation. So think about how the C value might stay the same or change. That normalized value might stay the same or change over the course of your simulation and why that might be the case. I hope this helped. Feel free to email me if you're having any problems with the assignment. And thanks for listening.